celebrating the Einstein Center. I, together with Avi, who is going to talk tomorrow, represent the Israeli neuroscience community, and we do have a close relationship with the people in Berlin. And this close relationship starts or been initiated and propelled by Uwe Heinemann, whom we all missing a lot. I hope that the new generation in Berlin will continue the close collaboration with the Israeli neuroscience community, because it's a really fantastic group of neuroscience here in Berlin, and I am usually not easily being impressed. So it's really a very nice center, and I found it out my previous visit here. Now for science. As you can see, we're going to talk about the cerebellum. The cerebellum is a big structure compared to the amygdala or even the hippocampus. Have far more neurons and connection and connectivity and function, whatever you want, and yet I am the only one represent cerebellar research here, which we have to think about that. One of the reasons they say people study the cerebellum, they don't like each other. And the argument in cerebellar research is huge. And that argument is hot and on the verge of violence. And you argue almost about everything. There's one aspect that everyone agrees. The cerebellum has something to do with timing. And if you ask me, the entire brain has something to do with time. There's nothing but time when we talk about the brain. It's how to generate impulse or signal at a given time. That's what the brain is supposed to do, at least in my opinion. So timing of motor activity, accurate timing of motor activity on a millisecond and 10 of a millisecond time window, it's the essence of cerebellar function. Everyone agrees. But more recently, you found that it's not limited to motor. And the timing function, not limited to the motor, I pick up some recent paper. I found it very interesting, which say we found significant activation in the olivocerebellar network comprising the inferior olive, vermis, and deep cerebellar nuclei, including the dentate nucleus during absolute duration-based timing. And the results of the fMRI, you can see the olive is labeled, the cerebellum is labeled, the back of the cortical cerebellum is labeled, and absolute duration-based time, it means that the person that we're looking on his brain is doing, he has to compare time interval in the auditory system and say if it's bigger or larger or smaller than the previous interval. This is the absolute duration-based time, and that was compared to another experiment when you give a background of constant interval, and only the last one can be bigger or smaller. This is another type of timing function, but then they found out that this type is mostly occur at the basal ganglia striatum area. So they conclude the inferior olive and the cerebellum act as a precision clock to mediate absolute duration-based time. And this is sensory function, it's not a motor function. Now what I want to ask is, okay, precision clock, what do we need for a clock? Before I go into what we need for a clock, what in the cerebellum generate this timing? It's the vermal area, the deep nuclei, and the inferior olive. And for a long time, the people defined the cerebellar module as the main circuitry of the cerebellar structure. And this is composed of the Purkinje cell, which I guess all of you know. It's a lot of neurons. It's the principal neurons of the cerebellar cortex. It's the only output of the cerebellar cortex, and unfortunately, it's an inhibitory output. And then we have the cerebellar nuclei and the inferior olive. The inferior olive is a group of neurons that are connected one to another by gap junction, and that's well known for many years. And they send the axon up to the Purkinje cell, what is well known as the climbing fiber synapse. And the climbing fiber synapse is one of the strongest, no, not one of them, it's the strongest synapse in our central nervous system. And from the Purkinje cell is going down to the deep cerebellar nuclei. Innervated, I put in this figure only two types of neuron. The small neuron is an inhibitor neuron that projects back to the inferior olive, and the large neurons are the ones that are going out of the cerebellum. So if everyone in the brain knows what happened in the cerebellum, is this through this output path from the deep cerebellar nuclei to the thalamus, brainstem, and other area. Now, we need a clock. Something in this system should work as a clock. So what do you need for a clock? What you need for a clock is a pendulum. Something will make movement at the right time. We don't have pendulum in the brain, but when you measure the activity in the inferior olive, and this is an example of recording simultaneously from two neurons in a slice preparation, you can see that it acts like a pendulum. It's going up and down synchronously within these two neurons. Occasionally, action potential is generated. Once it's generated, it's only going to be generated at the peak of the oscillation. So we assume that this is the pendulum of the clock within the cerebellum. We did a lot of work on this oscillation, and I'm not going to describe it. We worked on it for many years, and we suggested several possible models to account. All of them can be summarized as a property of a network of neurons that are electrically coupled. And that's what we have in the inferior olive, a group of neurons that are electrically coupled. Once they couple, they start to oscillate. A single cell will rarely oscillate, but once they are coupled, they will start to oscillate. So in order to make this clock to work, we just have to couple the neuron. And if we don't want the clock to work, we will uncouple the neuron. And that's what I want to describe in the next several slides. So first, first we want the clock to be stable, because if it's happened randomly, it cannot serve as a clock. And we want it to be stable. And you can see here that the oscillations are really stable for a very long time. And if you look on the autocorrelation function of this membrane potential, you see the accurate sine wave-like movement of the membrane potential. And the spectrogram shows you that in this case it's going on very stable to up to 2 minutes. I don't think we need more, but it can go on forever. It's not always look like a real sine wave. Sometimes you can see that it's kind of a beating oscillation, which I'll go back to that later. But this is most likely generated by a single oscillator. And as I said before, this single oscillator is a group of inferior olive neurons that are coupled together. Next, we want it to be synchronized, because if every neuron in the brain is working independently, we're going to end up with a terrible clock. So we measure from 2 neurons, and you saw it before, precisely accurate oscillation, and you do the cross correlation, you see there is a 0 phase difference. So this is a problem, because 0 Zs mean the resolution of the clock will be determined by this frequency, which is, in this case, it's in vitro study, is about 4 Hertz, and it can, in vivo condition, it's going up to 8, 9 Hertz. But it's still limiting the resolution. We're looking for 1 millisecond precision, and this will provide only tenths of millisecond. But not always they are exactly in phase. And sometimes, I will show you later, we have phase difference. And by playing with the phase between the oscillator, I can increase the accuracy of the temporal resolution of this system, because it's not only depend on the frequency, which is rather low, 10 Hertz, 100 milliseconds. It's not very accurate for playing the piano, for example. So if you use the phase differences, we can increase the accuracy of this clock. Now, we want to start the clock when we want to perform something. It cannot be that we should start work on a clock that keep ticking in the brain without resetting the clock. So we study how, in this system, we can reset the clock. For that end, we use the Thy1 mutant, which luckily, this is the inferior olive. There's no green part in the inferior olive. Everything else, you have green part. You should notice the pyramidal cell have a very strong labeling in the Thy1. If you look in a large gain into the olive, you see that the cells are dark structured. They don't express channel resorption. So if you turn on the light in this system, you are bound to activate only the green fiber, which we found that most of them are coming from the pyramidal tract. And saying that, this means that in this case, the motor cortex have direct access to our motor clock, if you want. So what happens when you turn on the lights in this? You indeed activate the synaptic input. If you make it strong enough, it's an excitatory synaptic input that occasionally generates an action potential. And the question now, what is doing to the clock? So you see that we turn on the light in 3 examples that we see here, and it doesn't matter when we turn on the light. Immediately after the light, it all starts all over again. So this little pulse of light resets the oscillation and determine, let's start the clock, or let's restart the clock, or let's adjust the handle of the clock. It's any way you want to look at it. So we studied it in very detail, and to study this in detail, we developed a system or measurement where we can characterize this phase resetting property. So you measure the time that you give the light pulse relative to the oscillation, and you measure the time from the light pulse to the next peak of the oscillation, and you calculate the average period of the oscillation, and then you can plot the time that you stimulate relative to the cycle and the time of the next peak. And when you get these red dots here, it means that it doesn't matter when in the oscillation we provide the input, the output will always occur at the same time. While if you don't have an effect, you're going down linearly, because the closer you get to the next peak, the smaller is the value of tau 2. So we have a method to somehow look at on the resetting system, and then we use the advantage of the optogenetic to study it systematically. You can see several traces recorded, and the light pulse is given here, and we got beautiful resetting of the system, and indeed we get a straight line on the plot. Next, we turn on the light only in this little corner of the visual field. Once you do that, it seems that nothing happened. Although we have a response, nothing happened. And when you do the calculation, indeed you get this diagonal line, which say there's no effect on the phase by the light. Now, interesting part, when you turn on the light on a little bit larger field, and when you do that, for the first quarter of the cycle, you get resetting. For the second part, it suddenly drops. The second quarter of the cycle, it suddenly drops to a low level. This might be an artifact of a measurement. And for the last part, it's diagonally going down. So depend on the input, you can completely reset the system, or you can partially reset the system. If we want it in behavioral terms, we want to continue a movement, we want partially to reset the motor system or the motor clock. If we want to initiate a movement from that point, we want to completely reset the clock. So we have a beautiful system, very accurate system, and as I said before, some of these inputs are originated in the motor cortex. It means that the motor cortex sends the information to the inferior olive to reset the clock. Now, what about starting and stopping the clock? Starting and stopping the clock should be very easy, because as I said before, we demonstrate that the oscillation is a property of a group or a network of electrically coupled neurons. So the only thing you have to do is to uncouple the neuron. So how do you uncouple the neuron? This has been suggested by Linus about more than 40 years ago, which means that you have two olivary neurons. They are connected by a gap junction, so current can flow from one neuron to the other neuron. Once you activate the inhibitory synapse here, current will leak out and nothing will get to the postsynaptic cell. So functionally, you are uncoupling the cell. You don't destroy the gap junction, not the protein involved. You just shunt the current and you prevent the connection or the communication between the cells. This theory will be based only on morphological findings, and you can see that the two dendrites of two olivary cells connected by gap junction, and this gap junction is surrounded by inhibitory terminals. It took another 15 years for Chris Dezel to find out the source of this inhibitory terminal is indeed the inhibitory neuron within the deep cerebellar nuclei, the one that I mentioned at the beginning of my presentation. So the inhibitory neurons in the deep cerebellar nuclei are the ones that control the coupling between the cells. So we went again to optogenetic. We injected channelrhodopsin to the deep cerebellar nuclei, and we look at what seems to be in the inferior olive. And indeed, we have a very nice specific labeling of the inhibitory neurons in the deep cerebellar nuclei, and have a huge number of terminals in the inferior olivary. So we go back to the slides. We turn on the light, and we see inhibitory input. Now, inhibitory input, in this case, we were surprised to find out that it's independent of the duration of the light. Make a short light, you make a long light, got about the same synaptic potential. I was puzzled by that. So we went and measured the activity in a single axon within this slice. And what you see is that you have it's extracellular recording, of course, of activity in a single axon. And you have something that looks like action potential. When you reduce the intensity of the light, you can see the delay increase until it's completely stopped. A single action potential. So we measure the activity in different duration. It doesn't matter. You can go up to a second of light. We have only a single action potential per light. Now, is that physiological property of this axon? I doubt it. You have to remember that the axon here is in a slice, have been cut from their father or mother, and you have a short axon, and this short axon does not respond with multiple spikes for a single pulse. So we are forced to go into train of pulses. And indeed, when you provide a train of pulses, you can generate something that looks like a steady state, a new steady state of activation of inhibitory input. And with this, we can try to find out what happened to the gap junction or what happened to the electrical synapse. And you measure from 2 cells, you inject iron in cell 1, you measure the response in the second cell, and vice versa. Its electrical synapse is going in both ways. And then you turn on the light and you measure again. And you see that the response in the postsynaptic cell are reduced. And you do that in many cells, and you end up with an average decrease of 50% in the coupling coefficient. That's very nice because it means that maybe GABAergic input really control the gap junction or the electrical synapse in the olive. But what it's doing to the oscillation. You see oscillating cell, you turn on the light, it stops. You go for a longer thing, it stops longer, and it takes him some more time to recover, and so on. So we have a method to turn off the oscillation or turn on, and the question is how specific it in space. So we go to record from a single cell, we turn on the light on the square around this cell that we measure, and we see that we completely block the oscillation. We turn on small portion, there's some reduced effect. You go to the green one, you get a little bit more effect, less effect than here. And then for the next one, you got complete blockade. And now the last one, we take it completely out of the area, and we do have a complete blockade of the response. That means that it has some sensitivity in space. The input from the deep cerebellar nuclei can control who is going to be connected. It's not a global effect. It can control who is going to be connected. And once they are connected, they will start to oscillate. And another example is when we record from 2 neurons, you turn on the light here, and you block the oscillation in both neurons. You shift the light to another place, and you block the oscillation only in one neuron, the black one. The red one keep oscillating in a different way, in a different waveform, but it keep oscillating. And this last thing is shown here in a longer sweep. You see, this is the control. This is a cell that shows beating oscillation. As I mentioned before, beating oscillation meaning that you have two oscillators with a little bit different frequency oscillating. And that's when you get beating oscillation. You turn on the light, you turn off one of the oscillators, not both of them, one of the oscillators, and you get a very clear sine wave-like oscillation. Well, turn off the light again, and that's coming back. It's very nicely organized in space by determining which neuron in the deep nuclei will be active or inactive, depending what you want to get. You can decide or organize the network within the inferior olive to match a certain behavior. So I want to go back to the title of my talk, which said, a model of pattern generator. And to generate a pattern of activity, to generate, not to change it, to generate it, you need a clock. So how this system of the inferior olive is generating the specific pattern that we want. And that's why I want to present in the next two slides. The first slide is dealing with the inferior olive. You can imagine that this is the input level of the inferior olive. The purple area is the area when we don't have inhibition. The rest is inhibited. So we have we organize the input in the olive in space. Once we organize that in space, we have only this group of olivary neuron will be coupled because they are the only one that don't have inhibition. They will be coupled. Once they will couple, they will start to oscillate. They will oscillate, assuming that it will generate action potential, and each oscillation in these four cells, we got a pattern of activity which depend, in this case, in the phase shift between the oscillator. And the output of the system will be kind of a pattern. Now, okay, we have a clock, and the clock can generate pattern of activity. How you put it in the context of the cerebellum. So let's say that a call for a pattern is sent from the brain to the cerebellum. And it said, we need now to play a certain music, we need a pattern to activate the finger. This pattern is coming into the cerebellum to what is known as a mossy fiber. And they going into the Purkinje cell. This is a very large system with billions of axons and hundreds of thousands of Purkinje cells. So the skull coming through the mossy fiber. And the Purkinje cell we made several years ago, we showed that they can exist in two stable states. They either can fire or to be quiescent. Now let's assume that this is true, because we still there are arguments about that. The call for input will be translated as some Purkinje cell to go into firing mode, the other Purkinje cell will go into quiescent mode. Now these Purkinje cells, as I said, are innervating the deep nuclei, and the deep nuclei, this will stop to work, and this will start to work because the Purkinje cell input is inhibitory. Now, this neuron projects to the inferior olive. The one that stopped to oscillate, to fire, means the inhibition is removed, and this group of red cells will start to oscillate, while the other group of cells receive a lot of inhibition, and they will stop to oscillate. So nothing will come out from the purple cell, but something will come out from the red cell. This will go back to the deep nuclei, and as you know, as I said at the beginning, this is the main source of the main path that lead the information or convey the information from the cerebellum to the rest of the brain, and what we got is the output. So I have a circuit that starts from a call-to pattern and end up with precise output pattern. Now, this, of course, has to be learned. You are not born with that. And the learning occurs here. And this concept that learning or plasticity occur in a parallel fiber prokinesil system is a very old concept. You learn it by experiment. You need the return output from the olive to confirm it, but the main output of the cerebellum is the climbing fiber output, if you want. I just want to thank two people for the work. There are many people did this work, really many people. And the last two are here on this figure. And Yarom, she's now in London in a postdoc. And Marilka was a postdoc in my lab, and she's now got a position in the Okinawa Institute of Technology. And Yarom grew up in a small village in Israel. And what they do in this village, they're growing olives. So that olive, beautiful, it's growing olive. So I got from Yarom this beautiful video clip. Beautiful video clip. When what you see in the video clip, once it will move, there's an olive tree. There's one network of olive connected through the branch to another olive. And in the middle, you have an input delivered to one of the networks. So once you deliver the input, it starts to oscillate. And the oscillation from one subnetwork is propagating to the other network. Exactly what we see in the oscillating network, going back and oscillate the other network. So what can you conclude? The beauty of this olive tree is that it's very easily explained by very good old physics. You have the coupling between the network, you have the oscillation going from one to another. In the brain, it's a little bit more difficult. So what do we conclude? The olive is an olive, and the last thing that we want to know, what the olive is doing in the martini. We are working on it. Thank you.